This chart shows you a general concept of the relationship between the service level that we provide to our customers and the cost that are induced by this service level. Of course, in this chart there are no actual data points. It's just a concept. On the x-axis we increase the service level. We start from 0% at the origin and increase it up to 100%. And on the y-axis we draw down the cost that are created by a specific service level. So you see, having a low service level, let's say below 50% in this graphic, implies a small amount of cost. But then, when we increase the costs, when we increase our service level, our costs rise exponentially. How can you see this in an example? Let's consider a call center that takes your calls, maybe the electricity company, the water company, a mail order company, you call a travel agency, whatever. So you call their call center, and the less you have to wait to get to talk to a human, the better, the higher the service level is. Now you can imagine if you have only one call center agent, and this agent is talking to one customer, another customer is calling, and this creates a lot of waiting time. So if we want to avoid the waiting time for our customers, then we need to hire more call center agents. And to make sure that there's little waiting time or no waiting time, we have to hire many call center agents. The principle is the same in the grocery store when you are waiting at the checkout counters, in particular when it's a very popular day. You have to open many checkout counters in order to avoid waiting of your customers, and the cost for the service will rise exponentially. Okay, this is one thing. Higher service level means an exponential rise in the cost for service. Let's look at another fact. So, for many businesses, the probability of sales follow a normal distribution. I'm thinking of, in particular, retail-based businesses, for example, an e-commerce shop for, in this example, books, electronics, makeup, beauty stuff, fashion, shoes, jewelry, whatever. So, and now in such a shop, we look at the number of orders we receive for any specific product. So let's pick one product and see how many orders we receive for this product every day. Then we can calculate the average of orders for every day for this specific item, and the average is shown here. This is the average number of orders we receive from a given product every day. We can also calculate the standard distribution. You know this from your basic statistic courses from school. You can calculate the standard deviation of the number of orders for every day. Though when these orders follow a normal distribution, which is the case in many situations, then we know that 68%, roughly 68% of the orders lie within this area. They are -1 standard deviation away from the mean and +1 standard deviation away from the mean. So that means in 70% of the days we receive these numbers of orders in this interval. If we expand this interval and look at a deviation of 2 standard deviations, then we know by the law of the normal distribution that more than 95% of the orders are within this interval. Yeah? And when we increase it to 3 standard deviations, then we know that 99.7% of the orders lie in this interval every day. And given this knowledge, now we can decide how many of this products, how many items of this products, how many pieces of this products should be on storage, though that we immediately can fulfill this customer order. Yeah, though by using this knowledge, we can decide how big our inventory should be for every given product. We can fine-tune this analysis. Of course, we are interested in those orders that would exceed our inventory. Yeah, though we do not care very much about orders that are lower than our average daily orders, but we care a lot about those orders that are higher than our daily average. Though that means we only need to look at the right side of this diagram, of this chart, right to the average, and by the law of the normal distribution, we can make the following statements. The average order, X with an overline, is achieved in 50% of the cases. Let me phrase it differently. The expected daily demand for an item, X bar, is less No, let's start again. The expected daily demand is less than X on 50% of the days. The expected daily demand plus 1 standard deviation is less than 85% of the days. And our daily orders will not exceed X bar plus 2 standard deviations on 98% of the days, and it will not increase X bar plus 3 standard deviations on almost 100% of the days. So you see, if our inventory level, if the number of items is equal to the expected demand, then we are able to fulfill 50% of our orders. If, on contrast, our inventory level for this item is equal to X bar plus 2 standard deviations, then we are already able to fulfill 98% of the orders. And by going for 3 standard deviations, we can achieve almost 100% of the orders. And now the big question is, how much costs do arise if we go from 98% to 99.9%? Is it still useful? Does it create additional benefits for us? This is a decision we have to make for each group of customers and each group of items.